How does linearization work in mechanical engineering? Imagine trying to understand a complicated machine that moves in unpredictable ways. Instead of tackling its full complexity, what if you could simplify it just enough to see how it behaves near a specific point? That's where linearization comes into play. It's a technique used in mechanical engineering to make analyzing complex systems much easier. When systems behave in nonlinear ways, their equations can be tough to solve directly. Linearization helps by creating a simpler, linear version of those equations that works well close to a specific operating point. In system modeling, engineers often start with the nonlinear equations that describe how a machine or system moves. These equations come from principles like Newton's laws or Lagrangian mechanics. The challenge is that nonlinear equations can be difficult to analyze or control directly. To fix this, engineers find a point where the system is at rest or moving steadily. This is called the equilibrium or steady-state point. They then look at how the system behaves when it is slightly disturbed from this point. The next step involves calculating the derivatives of the equations at that point. These derivatives tell us how sensitive the system is to small changes. Think of it like measuring the slope of a hill at a specific spot. These derivatives for matrices called Jacobians, which describe how the system responds to tiny deviations. Using these, engineers build a set of linear equations that approximate the original nonlinear system near that point. This process is called taking the first-order Taylor series expansion. Once the linear model is ready, it can be used for many practical purposes. For example, it helps in stability analysis, where engineers check if small disturbances will die out or grow over time. It also makes designing controllers easier. Instead of working with complicated nonlinear equations, engineers can use well-known linear control techniques like proportional integral derivative controllers or state space controllers. These controllers can then be tuned to keep the system stable or to follow a desired path. Linearization also speeds up simulations. Instead of solving complex equations every time, engineers can run quick simulations around the operating point. This is especially useful in the early stages of design or when testing different control strategies. Additionally, linear models are helpful in system identification, where engineers estimate system parameters based on experimental data. They fit a linear model to the data to understand how the system behaves locally. In advanced topics and professional practice, linearization is a key step in understanding how systems respond to small changes. It allows engineers to analyze stability, design effective controllers, and predict system behavior without getting lost in the nonlinear complexity. By approximating nonlinear systems with linear models, mechanical engineers can make smarter decisions faster and more accurately. This approach is fundamental in system dynamics and control, making it easier to manage even the most complicated mechanical systems.